Alrighty there. Good afternoon, lads and ladies. Welcome back. Today, we're going to take our next step into integration land. And this week is going to be a relatively gentle week because we lost yesterday, or not yesterday, Monday. I am going to cover a little bit less material than I normally would this week. That's okay, because we're still kind of getting comfortable with integration. The big thing today is we're going to introduce the notation for indefinite integrals, which we've talked about just the tiniest little bit when we were talking about a place in the textbook you could find tables of antiderivatives. Today we will kind of formally explore that, and then the more exciting topic for this week is something called the net change theorem, which is really not related to indefinite integrals. It's kind of a funny way the textbook chops this stuff up, but it'll be okay. So here we go. This, of course, is MAC2311, section number 004, which is a Calc 1 class. And the date today is the 6th of April, 2022. Today on the chopping block, indefinite integrals. Which is section 5.4, and also the net change theorem. Which is section 5.4 as well. I could not possibly explain why the author chose to put these two things in the same section, beyond saying maybe having a whole section dedicated to indefinite integrals just felt like it was too short. So they said, fuck it, let's cram this other shit in there. No harm, no foul. An indefinite integral is, well, let's introduce the notation. So not notation or definition. The symbol, this thing, remember we call the integral symbol. Or integral sign. And when written, when writing an integral without bounds, we call it indefinite, which is to contrast it with the integrals that you see written with bounds, right? Like integral from 0 to 1 or something. So this thing, the integral of, say, f of x dx, with no numbers written below or above the integral sign, is called the, leave some space over here, is called the indefinite integral of the function f of x done with respect to x. And when we say done with respect to x, we don't mean regarding x highly, right? We don't mean exalting x or treating x as though it deserves a bunch of respect. We mean we're treating x as the variable. Just like when we talk about differentiating with respect to y, or with respect to t, or with respect to x, integrals can also be done with respect to different variables. This is all well and good, but it doesn't really tell you what the fucking thing is or how to compute it. But we did mention this the other day. This is just the notation that's used to describe the most general antiderivative of little f. Oof, sorry. So this would be equal to capital F of x plus c, where big F prime is little f. So this is just a notation for the most general antiderivative of the function little f. That's all. So what this allows us to do is kind of merge together the two concepts and notations that we've been playing with regarding integrals. When we've been doing integrals so far, they've always been a definite integral, which we think of as an area bounded by a curve over some interval. And we learned that we solve those by finding antiderivatives and then plugging in the bounds and subtracting what we get. That was the second fundamental theorem of calculus. Because the definite integral as its main step is like find an antiderivative, then plug in the bounds and subtract, the integral symbol without bounds is kind of a convenient logical notation for find the antiderivative. This doesn't involve the f of b minus f of a. There's no plugging in because there are no bounds to plug in here. Right, so it's just because we didn't previously have a nice notation for the antiderivative of. If I wanted to write something like the antiderivative of x squared, I had to use this cumbersome notation where I call x squared little f, and then I could say, okay, now big F is this. This allows us to write that sort of thing more nicely. Let me just show you a few very simple examples to make sure we're comfortable with the notation. Then we'll explore some problems before talking about the net change theorem. So we mentioned x squared a minute ago. The indefinite integral of x squared, you would apply your power rule, you get 1/3 x cubed, and then slap on your plus c. The indefinite integral of e to the x plus secant squared of x dx, and it is still very important to write the dx, would be the most general antiderivative of e to the x plus secant squared. We've learned previously that you can anti-differentiate each piece on its own if they're being added or subtracted. So what is an antiderivative for e to the x?
E to the x plus c.
We could write separate plus c's for each of them, but I'm just going to write 1 plus c at the end. Two arbitrary constants added together, still just another arbitrary constant. So what would be an antiderivative for secant squared?
Tangent.
Very good, tangent, because the derivative of tangent x is secant squared x. And I'm glad, I appreciate the comment there that we could write a plus c with each of these. That is definitely true. I could split this up, and we're going to give a theorem in a minute that describes that explicitly, and write, e to the x plus c1 plus tangent x plus c2. But c1 and c2 are meant to be arbitrary constants, could represent any real number. So having two separate arbitrary constants added together is the same as having one arbitrary constant, just labels the big C as C1 plus C2. So generally when we do these, no matter how many pieces they have, we only write 1 plus C at the end. All right, just to see how well we've internalized our antiderivative results. Anybody help me with this one?
Arc sign.
Excellent. Who was that? Ethan. Ethan, I owe you a beer or something. Nicely done, sir. Arc sign. Yes, this is the inverse sine of x plus c, which you can also write as ARC, sin of x plus c. This is the inverse sine function, because the derivative of the inverse sine function, arcsine of x, is 1 over the square root of 1 minus x squared. All right, that's what indefinite integrals are. It's actually not anything new, it's just new notation. Hence the waffling on notation versus definition up here. Just new notation. This does mean we've got an excuse to practice more and more of these. I am going to explicitly state a theorem here, which we have mentioned in the past, but we didn't have a convenient notation for it. The properties, indefinite integrals. I'll abbreviate indefinite indef, if that's okay with you. He says, as though you're going to protest. All right. This is what we said a second ago. If we're trying to find an antiderivative for a sum of two functions, we know from section 4.9 that we can find an antiderivative for each of them on their own and then add them up. What this means is that indefinite integrals can be split up over addition like this. And this really is the nicer notation for describing that result. And as with so many things, if it works for plus, it works for minus. I'll call this property 1. You can guess what's coming next. If c is a constant, then the indefinite integral of c times f of x dx is c times the indefinite integral of f of x dx. And I've said it a million times, every time we've introduced an operator, these two things together mean that this operator, the indefinite integral, is a linear operator. Linear operators are the bread and butter of the mathematical world. Thank goodness this is one of those. I don't have a list of like 10 other things here, thankfully. This is the end of the game. There are, of course, lots of antiderivative formulas you can and should and frankly must remember. And if you recall, those are listed. This is where we talked about notation once before, here. So these are all of the indefinite integrals that I expect you to know by heart. You can make flashcards for them if that's your vibe, if that's what you like. I would say this bottom one here, don't worry about the hyperbolic trigonometric functions. I'm not going to beat you to death on those. But definitely make sure that you know everything else. Know them cold. Okay, we're going to do some examples here because why the fuck not? And then we're going to talk about that thing called the net change theorem. Before we do that, any questions on any element of this table? Is there anything here that is we'd like to remind ourselves why it's true? Anything about the notation? Okay. Example time. We can do this one. Actually, we did sine over cos squared the other day, didn't we? Similar enough to this. Let's do something like that. I'm going to show you the workflow now slightly differently than we had been doing them before, more in line with what we do for definite integrals to kind of illustrate the utility of the notation. In the past, we said, okay, we can kind of think about each of these things on their own, and that's 100% true. But as the problems get more and more and more complex, it becomes more and more worthwhile to actually use notation to split things up. So my first step here, well, it might seem a little bit silly, and indeed we won't always do this. Will be to use those properties to tell my reader that the way I'm attacking this problem is by approaching each piece on its own. The 2 is going to come along for the ride. The indefinite integral of x cubed would be the most general antiderivative of x cubed, which is 1/4 x to the 4. And I'll go ahead and write a plus c1 here. And then we would have minus 3 times the indefinite integral, or most general antiderivative of square root x, which is x to the 1/2. We will again use the power rule. So we add 1 to the power 1/2. 1/2 plus 1 is 3/2. So we'll have x to the 3/2. And then we know we would divide by 3/2. That's the same as multiplying by 2/3. So at this point, I am going to go ahead and start doing that when we have fractions as powers. Rather than dividing by that fraction, I'll jump straight to the multiply by reciprocal. And we can write plus c2 here if we want. Finally, this last guy is 2 times the most general antiderivative for x1 over x squared plus 1. What is this guy? Did we mention this guy?
Arctan.
Arctan, very good, the inverse tangent function. And if you prefer to write arctan, that's fine. I have become accustomed to the inverse notation like this. Either one is fine. So if you're being very, very formal, this would be the logical flow. You split up the integral, attacking each piece on its own, popping out the associated constants. You can give each one their own arbitrary constant because you have 3 integral symbols here. It is reasonable to expect 3 constants. 2 times 1/4 is 1/2, so I'll have 1/2 x to the 4th. I'm going to group all the constants together at the end. 3 times 2/3 is 2, so I'll have minus 2 x to the 3/2. And then 2 times the inverse tangent of x. And then you have your plus c1 plus c2 plus c3. But I could relabel all of these as the single arbitrary constant c. So the nice way to write your final answer here, which you probably could, with the practice you've had at this point, jump to straight from the start. Would be written like this. Here's the deal. As we develop more and more integration or anti-differentiation skills, we won't be using the same rules on all of the pieces, right? These 2 guys were a power rule, and this one, we popped out the constant, and you know that this is the derivative of arctangent. So I genuinely do believe that all of us could, given a little bit of time to stare at this, write down the answer straight from this form. But down the line, we're going to have tools like use substitution, integration by parts, partial fractions, trig sub, all this other good shit. And you may be given an integral like this where this piece requires u sub, where this piece requires trig sub, where this piece requires partial fractions. So going through the notational step of splitting up the integral and writing it as 3 separate integration problems is not only at that point useful, but necessary, because each of those will be attacked differently. She don't have to wait. All right. Any questions on this guy? A healthy chunk of your homework this week is just calculate this indefinite integral or calculate this definite integral. There are definite integrals in here as well, just to keep your brain sharp on that stuff. I think it would not be a bad idea. I know it might seem redundant to look at one more where we have to do some kind of sneaky algebra. Before we get to the net change theorem, let's try to find something cool down here. Oh yeah, there's one we haven't used. All right. I'm gonna tack a little extra something in here. Oh, sorry. Make this a T. So I want to evaluate this indefinite integral. And the thing inside, the integrand, is a difference of two functions, at least at a glance. The first function is 2 to the t times 1 plus 5 to the t. The other guy is 1 over t to the 5. Again, I think it's not a bad idea to split this up as the integral of 2 to the t times 1 plus 5 to the t dt minus the integral of 1 over t to the 5 dt. And in that first integral, there is more algebra that we need to do. I need to distribute this 2 to the t over the addition here. I cannot integrate a product of two functions, but I can integrate a sum of two functions. So when I do that, I'll get 2 to the t plus, I'll write this as 2 to the t times 5 to the t for now, dt. And then the 1 over t to the 5, I'm going to write as t to the negative 5th dt. And it is similarly important that we rewrite 1 over t to the 5 as t to the negative 5. You cannot just integrate t to the 5 down here. All right, you can't say this is 1/6 t to the 6 all downstairs under 1. That doesn't work, because just like you cannot integrate a product of functions, you cannot integrate a ratio of functions by integrating the top and bottom separately. A few possible sticking points exist. What is 2 to the t times 5 to the t?
Is it 10 to the 2t?
Almost. This is the same as 2 times 5 to the t. So it's just going to be 10 to the t. Remember, if we have like bases and the same exponent, like 2 to the t times 2 to the t, that would be 2 to the 2t. You add the powers. If you have different bases and the same exponent, right? If I wanted to raise 2 times 5 all to the t, I would do that. That's 2 times 5, 2 times 5, 2 times 5, all t times. That's the same as 2 to the t times 5 to the t by commutativity. So this piece I can rewrite as 10 to the t. And we can split that integral up a little further. So this is the integral of 2 to the t dt plus the integral of 10 to the t dt minus the integral of t to the -5 dt. Integrals like the first two, I love giving these to very confident Calc 2 students in the beginning of the semester, because nobody remembers how to do this shit. Everybody remembers how to integrate e to the t, but just like people tend to forget how to differentiate things like 2 to the t, forgetting how to integrate them is fairly common as well. Can anybody help me with an antiderivative for 2 to the t?
Is it 1 over t plus 1, 2 to the t plus 1?
If 2 were the variable and t were a constant, yes. But 2 is a constant and t is the variable. So a good comment here. These are not power rule integrals because the variable is in the exponent. So the power rule says, I've used it many times, but this says that t to the n, if you integrate that dt, would be 1 over n plus 1 times t to the n plus 1 plus c. But the power here has to be a constant, and the base has to be your variable. In other words, this applies to power functions, things like x squared, x cubed, and so on. If you want to give it a name, we can call it the exponential rule. It says if you want to integrate something like b to the t dt, where b is a constant, you will get b to the t divided by the natural log of b plus c. And we can think about why that's true. But first, let's go ahead and write down the result. So if we trust the recipes on the page here, these two are both exponential rules, and this guy is a power rule. So this will give me 2 to the t divided by the natural log of 2. I'm not going to write all the little c's. I'll just write the one c at the end, and it's okay for you to do that also. Plus integral of 10 to the t following the same rule will be 10 to the t divided by the natural log of 10 minus the integral of t to the -5. We have to add 1 to that power. -5 plus 1 is -4. So this is going to be -1/4 t to the -4. And then I'll write my big plus c at the end here. There is a smidge of housekeeping that we can do. So 2 to the t over the natural log of 2 plus 10 to the t over the natural log of 10 plus 1 over 4t to the 4. Plus. Just cleaning up that last piece. Before we move on, let's take a look at the exponential rule, because it's not something we've proved. It is in our table there, it is in our recipe book for antiderivatives, but you ever get to the bottom of a cup of coffee and realize there's some nasty looking shit down in there? This is not your normal nasty shit either. This is some, I might want to go drink some Lysol nasty shit. All right, we'll do that after class. I can say, recall that if I have e to the cx and I want to differentiate that by the chain rule, this is e to the cx times the derivative of cx, which is c e to the cx. The trick for differentiating something like b to the x was to rewrite it in this form. And it's a very sneaky trick. I can write this as e raised to the power of the natural log of b to the x. Do you guys remember this from section 3.4? So anything can be written as e to the natural log of that thing, any positive thing, because the e and the ln cancel. Then, by the properties of logarithms, this is e to the x times the natural log of b, all prime. And now this thing is this thing. I'm trying to differentiate e raised to the power of x times a constant. So the natural log of b here is a constant playing the role that c plays here. So this gives me natural log of b times e raised to the x natural log of b. The natural log of b is going to chill out front. And then e to the x ln b is the same as b to the x. So what this means is that the derivative of b to the x is b to the x times the natural log of b. This is a result that we cooked up in the past. So now if you integrate on both sides, you'll get that the integral of b to the x dx, well, if the derivative of b to the x is b to the x times the natural log of b, then the integral of b to the x must be 1 over the natural log of b times b to the x plus c. Right? Because if you were to differentiate this, if you were to differentiate the right-hand side, c differentiates to 0, b to the x differentiates to ln b times b to the x. So this piece would become ln b times b to the x. And the ln of b would cancel with the 1 over ln b here, giving you b to the x as desired. So we've kind of pointed to this in the book a few times, but I never proved it. This is definitely on your list of antiderivatives you need to know. The truth of the matter is that these sort of things don't show up a lot. Pretty much every time, especially in calculus, that you work with an exponential, the nice way to work with it is to write it as like e to the something times x. But they can be a source of kind of stumpy problems, you know, true-false problems, where it's like, oh, if you know this, it's easy. If you don't know this, it's hard. I tend to not favor those questions, but in case you encounter them, here's the result. Questions on the problem above or the rule discussed below? Okay. Let's talk about the net change theorem. This is one of those things that when you just state it in terms of definitions and symbols, it's like fucking duh. But if you're asked to think about it a little bit more deeply, you can see that there are some subtleties. I mentioned last week that if you do a definite integral of a velocity function, and that velocity function is always positive, then the output from the integral from t equals a to t equals b of v of t will be the distance traveled by whatever object had that velocity. The deeper, more true story is that the integral, the integral from a to b of f primed of x dx, following the second fundamental theorem of calculus, you would find an antiderivative for f primed. Well, that's just going to be f. And then evaluate that between bounds. So you get f of b minus f of a. It's really just the fundamental theorem of calculus rewritten, where instead of like little f and big F, you have little f primed and regular little f. Of course, regular little f is an antiderivative for f primed. F primed is by definition the derivative of f. So just restating FTC2. But the object on the right over here has a special name that you may recall from the very first few weeks of pre-calculus. This is the net change in f, or say in f of x, from x equals a to x equals b. We use this when introducing average rates of change. We talk about net change, how much did the output change, and then average rate of change, how much did the output change when divided by the change in inputs. And that's kind of a warm up to talking about derivatives. Here we're looking at it from the other angle. We now know all about derivatives, and we're saying if you integrate the derivative over the interval ab, then what you get out is the net change in f from a to b. I know it doesn't feel deep right now, but let me give you an example. If, say, well, let's start with the physics one. If v of t is the velocity of an object at time t, then the integral from a to b of v of t dt would be, there's kind of two different notations for this. I'm going to use x of t for the position. Sometimes the book uses s of t. So down here I'll say where x of t is the position function. And this would be x of b minus x of a. And this stuff is the net change in position, which is called the displacement. And I'm saying displacement, and I'm avoiding the word distance very carefully here for a good reason. If I leave my house, walk to the grocery store, and then walk home, I have definitely covered some distance. But I ended up at the same place I started. So my net change in position is 0. If you do a round trip, you go somewhere and come back, then your x of b and your x of a are the same position. So your displacement is 0. But your distance traveled is certainly not 0. Maybe it's a mile to the grocery store. I've walked 2 miles. My distance traveled is 2 miles. But my displacement is 0. So displacement in simple English is how far you ended up from where you started. And just to be clear, displacement can be negative, can be 0, and can be positive. If you end up behind where you started, we would say your displacement is negative. If you end up exactly where you started, we would say your displacement is 0. And if you end up in front of where you started, we would say your displacement is positive. And the important note here displacement is not necessarily equal to distance traveled. If your velocity function is always positive, if you're always moving in the same direction, you never turn around and come back, then your displacement and your distance traveled will be the same. If, however, your velocity function is sometimes positive and sometimes negative, you spend some time walking in the forward direction, sometime walking in the backward direction, then your displacement and your distance traveled will not be the same. I don't know why I always forget whether the word traveled has 1 or 2 L's in it. Other examples, your book has a few cutesy ones. Mass cost, where is it? Related volume, yeah. If capital V of T is the volume of water in a tank at time T, then capital V primed of T would be the rate at which water is, depends on whether water is flowing into or out of the tank. And thus, the integral from A to B of capital V primed of T dt would be capital V of T evaluated from A to B, which is capital V of B minus capital V of A. What would this represent? In terms of the water in the tank? Let's pretend I've got a hose that's filling up a tank here. V primed is how fast water is coming in. It is a rate of change for the water in the tank. So this would be the net change, the volume of water in the tank. i.e., how much water did you add from time t equals a to t equals b? Right? Capital V of A, this is the amount of water that was in the tank at time t equals a. It's how much water you started with in the tank. V of B is how much water was in the tank when at time t equals b, when you're done filling. So if you take V of B and you subtract V of A, that's how much water you added between the times A and B. You can probably imagine there are a lot of application problems, a lot of real world problems where interpreting the definite integral as a net change is useful. And the most obvious one is physics, finding displacement or distance traveled. So I want to talk to you a little bit about finding displacement. We're going to do some calculations. And I also want to talk to you about how to find distance traveled, right? Because displacement isn't always the same. Is there some way I can actually find the distance traveled if my velocity is not always positive? Okay, other applications include things like charge density or reaction speeds in chemical reactions, or how quickly your body processes a drug in medicine, right? Like if you inject a patient with a certain amount of some drug and you know their body eliminates that drug at a certain speed, you can use these integrals to calculate how much of that drug is left in their body some number of times, some number of hours later. And that can tell you when to redose the patient with the drug. These sort of calculations are actually pretty important in medicine. So let's talk about displacement versus distance. If an object is always moving in the positive direction, and this would mean, i.e., V of t is always positive, then displacement and distance are equal. All right, and the picture here is not a very exciting one. Here I am at time t equals a, and I just walk in this forward direction the entire time. Here I am later at time t equals b. My displacement is my position here minus my position here. If the object changes direction, though, i.e., V of t is not always positive, then displacement is not equal to distance. So maybe I start over here at time t equals a, and walking in the positive direction for a long time. But then I turn around and I come back this way for a little bit. And I'm here at time t equals b. My displacement is the distance from where I ended up to where I started. But my distance is this plus this, call this d1 and d2, the distance would be d1 plus d2, which is much larger than, in this case, the displacement. And it is true in general that distance is always greater than or equal to the displacement. They're equal if and only if v of t is monotone. V of t is always positive, let's say. Is the picture here making sense? How far did I walk? Well, I walked this distance plus this distance. So my total distance traveled is this plus this. What is my displacement? Well, it's how far did I end up from where I started? It's just this distance, which is strictly smaller. And displacement will always be the integral of your velocity. Distance traveled will be the integral of kind of the velocity function if it were always positive. I'm going to write some stuff down here that seems silly, and then I'm going to give you some formulas, and then we'll do an example. So we said it already, displacement is the integral from a to b of your velocity function. Distance is the integral from a to b of an always positive version of your velocity function. Okay, if I give you some function and I say, find me a version of that function that is always positive, what does your brain want to do?
Absolute value.
Hell yes. To get your distance traveled, you don't integrate the velocity. You integrate its absolute value. I'm going to give you another picture here in terms of graphs that I hope will help you understand why, but intuitively. The integral is going to measure this as positive and this as negative. So when you do the displacement integral, the regular integral of v of t, it's going to measure this distance as positive, this distance as negative. So when you subtract those, when you combine those, you just get this. If I want to avoid that, I need to measure this distance as positive and also force this to be measured as positive. And that's done by changing the sign of v of t during whatever time interval is associated with this motion to kind of flip this part around and pretend like my dude kept walking that way. Let's look at an example. Sorry, we said we'd look at a general picture of a graph. So here is a graph of some velocity function. This is my t-axis. And maybe I do something like this. And maybe B is here. Maybe A is here. So here is a not always positive velocity function. let me label each of these little regions here as having area A1, area A2, and this little sliver in here we say has area A3. I'm also going to designate X values here. I'll call this C and D, where my velocity function goes from positive to negative or from negative to positive. From A to C, the object is moving in the forward direction. From C to D, the object is moving backwards. And from D to B, we're moving forwards again. So my displacement would be A1. I moved forwards by A1 minus A2, because I moved backwards A2, plus A3, because now I'm going forwards again A3, and I'm trying to find out how far I am from where I started, not the distance I traveled. So I walk to the right some amount here, and then I turn around and walk back to the left some amount here, and then I turn around and walk to the right a little bit more. And this would be the integral from A to B of your regular velocity function. Because you know that the integral measures stuff beneath the x-axis, or beneath the horizontal axis, I should say, as negative. But your distance even though you're moving backwards here, you're still covering ground. I shouldn't subtract that from the distance I moved forwards in the first place. If I'm just trying to measure how much ground or distance I covered, this should be the straight up sum, A1 plus A2 plus A3. And this would be the integral from A to B of the absolute value of V of t dt. And you might be wondering, well, how the fuck does one compute such an integral? Like if V of t was t squared minus 2t, how do you integrate from A to B something like the absolute value of t squared minus 2t? The answer is you split it up. You split it up using the property that we talked about last time. Integral A to B is integral A to C plus integral C to B. In this case, we would split it up as the positive integral from A to C of V of t dt. This piece is already positive, so I don't need to do anything with it. I just integrate V of t from A to C, and that will give me A1. The area A2 here is beneath the horizontal axis, so if I just integrated V of t from C to D, that would give me negative A2. I want to make that positive, so I have to subtract the integral from C to D of V of t dt. And then finally, I would add to that the integral that gives me this area, which is the integral from D to B of V of t dt. In short, how do you integrate an absolute value function? You split it up. You look at where the function inside the absolute value is positive, and in those cases, you leave it alone. You look at the places, t values in this case, where the thing inside the absolute value function is negative. And there, you negate the function to make it positive. Let me give you just a second to chew on that. Any questions about where this recipe is coming from? Okay. So these you want to hold on to. Tuck them somewhere you remember. Displacement is the integral of velocity. Distance is the integral of the absolute value of velocity. Let's start gently. Suppose a particle is moving on a straight path with velocity v of t equals, let's just say t minus 2. Find both the displacement and distance from time t equals 0 to t equals 4. I'm going to set this up and solve it the way I would expect you to solve it on an exam or in the homework. And then we're going to explore a little bit more deeply why it's set up that way. And then we'll look at a harder problem. First, the displacement. We know that that's the integral from a to b of my velocity function v of t dt, which is the integral from 0 to 4 of the function t minus 2 dt. Calculate your antiderivative. When we plug in 4 here, we get 1/2 times 4 squared minus 2 times 4. When we plug in 0, we get 1/2 times 0 squared minus 2 times 0. Clearly, that's all 0. 4 squared is 16. 16 times 1/2 is 8. 2 times 4 is also 8. So my displacement is 0. The distance would be the integral from a to b of the absolute value of the velocity. Which is the integral from 0 to 4 of the absolute value of t minus 2 dt. And to do an integral like this, I strongly recommend graphing the inside of the absolute value. Here it is. All right, it's a line with slope 1 and y-intercept -2. Specifically, it crosses over the horizontal axis, the t-axis, right there when t is equal to 2. So why did that first integral come out to 0? Well, because the area down here cancels perfectly with the area up here. In other words, what my dude did is he walked backwards for a little bit and then turned around and walked forwards that exact same amount. If you want to try and read as much qualitative information out of this as you can, my dude started off walking at like -2 meters per second, so going backwards at 2 meters per second. And then he slows down, stops, turns around, starts walking forwards, starts off walking slowly and then faster and faster and faster. The amount of distance he covered walking backwards is this area. The amount of distance he covered walking forwards is this area. We could compute this using geometry, but the point of this exercise is to get you practice handling these sort of things algebraically. So I'm going to do that. I split this up as the integral from 0 to 2 of the negative of this thing. So I'm going to put a negative out front here. T minus 2 dt. Plus the integral from 2 to 4 of t minus 2 dt. So you split up the integral. Wherever the inside of the absolute value was negative, you negate the integral to make it positive.
And without graphing, there's not a real good way for us to like know that.
Pretty much. Now, what I'm doing here, an alternative approach would be to make a number line for v of t. Right? You find where v of t is positive and where v of t is negative, then you just negate the integrals that come from the part where v of t is negative. That would also work. So I know that v of t, t minus 2, goes from negative to positive when t is equal to 2 by setting t minus 2 equal to 0. And then you could test a point or use multiplicities and end behavior to figure out that my velocity function is negative from 0 to 2 and positive from 2 to 4. And that would also be enough to tell you how to do this split. But I strongly recommend drawing the graph.
Thank you.
Of course. Now I'll have negative 1/2 t squared minus 2t from 0 to 2 plus 1/2 t squared minus 2t from 2 to 4. And as we suspect from the picture, these are going to come out to the same number. When I plug in 0 here, I'm definitely going to get 0. So I'll just do the calculation when we plug in 2. We actually, did we do that already? No, we haven't. So this is 1/2 times 2 squared minus 2 times 2. And then from this guy, I have 1/2 times 4 squared minus 2 times 4 minus 1/2 times 2 squared minus 2 times 2. I'm not showing the work for plugging in the lower bound from the first bracket because when you plug 0 in here, definitely everything is 0. Right? We did do that already. Everybody good so far? So if I just continue with this evaluation, clean things up, have a negative of 1/2 times 2 squared is 1/2 times 4 is 2, minus 2 times 2 is 4. So I have the negative of 2 minus 4 plus 4 squared is 16, 1/2 of 16 is 8, minus 8. So right here, the 8 minus 8 minus 1/2 times 2 squared is, again, 1/2 times 4 is 2. And then 2 times 2 is 4.
I'm sorry, can you, the step before where you, I can see why you did the first, yeah, that. But the second part, I don't understand why you subtracted that second part of the second part.
So when we have the evaluation bracket, like some function and then evaluation from A to B, that means we're going to plug in the upper number here, and that's what we have here, and then subtract what we get when we plug in the lower number here.
Oh, okay, thank you.
Yeah, I just got sloppy. I didn't write the 0 part from the first one because I knew it was going to be 0. So I'm plugging 0 in for both of these, and I didn't have the space to do it.
Oh, that's okay, thanks.
Yeah, no problem. So then altogether here, I have the negative of -2 plus 0 minus -2. And you can see the minus signs really pile up. You need to be very careful. There's another reason good notation is important. -2 is 2, plus 0 minus -2 is also 2. So this is 4. So my dude walked backwards 2 meters and then forwards 2 meters. So his displacement was 0. He ended up where he started. But he walked 2 meters in one direction and then 2 meters in another direction. So the total distance he traveled is 4 meters. Does that make sense? Everybody nails displacement integrals. Distance integrals are a little harder. And the deeper truth is that distance integrals are far more important. Down the road, you'll be replacing these with norms of vectors and finding things like arc length. So this is a good place to sort of warm up this physics brain. We are at 3:15 now, so rather than going through a full, more challenging example, I'm going to just set up the more challenging example. And let's do something like this. So I'm going to set up an integral for the distance covered by an object moving on a straight path with velocity v of t equals t squared minus 3t from time t equals 0 to time t equals 5. I do think it's worthwhile to sketch the velocity function. It does not need to be a perfect graph. We're really just trying to figure out where this thing is positive and where it is negative. But if you can get the shape approximately right, the area is reasonable, it can be a big help. So if I factor a t, I see that my velocity function is t times t minus 3. So let me mark out here 1, 2, 3 along my t-axis. And I'll go ahead and add the 4 and 5. Because v of t factors as t times t minus 3, I know that the graph will cross the horizontal at these 2 points. Because it's a quadratic, I know there's an axis of symmetry. I have no idea where this vertex is in the vertical, but I'll just plop it halfway between the roots. I'm not even specifying a scale for my vertical axis, so it really doesn't matter. I am going to run out of space over here again. Something like this. So again, homeboy starts out walking backwards. All of this is my dude walking backwards because the velocity function is negative. We're going very slow at the start, and then we speed up, going backwards, faster, 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 and then we're going really fast backwards, and then we start slowing down, still going backwards, 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 slower, 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 come to an instantaneous little stop where we turn around and then start running forwards. The distance is the integral from 0 to 5 of the absolute value of t squared minus 3t dt. And the graph tells me how to do the split. I need to split at 3. So this will be equal to this region is negative, the 0 to 3 region, so I negate it to make it positive. And the whole idea here is that the absolute values go away when I do this. I no longer have an absolute value. I just have t squared minus 3t dt. And then I add to that the integral from 3 to 5 of t squared minus 3t dt. And because we're now 5 minutes over, I'm not going to push and evaluate these integrals, but I'm sure that anybody here could evaluate these integrals. They're power rule integrals, is nothing crazy. Drawing the graph strictly necessary? No. If you find another way that works for you, specifically making the number line or a sign chart, right? Sign charts also work. It's the same sort of thing we did when we were graphing and finding mins and maxes, only we're doing it for the function itself. You can do that here as well. But however you get there, we got to get from being able to take things like this and splitting them into things like this. All right, that's where I'm going to leave it for today. Next time, we're going to talk about some more applications. I'm going to show you something called an initial value problem. Those are quite exciting. Is there anything you guys would like to discuss before I let you go? All right, then we'll go ahead and end it here. Oh, I see something in the chat. Next exam, that's a good question. So we have to cover section 5.5 and then 6.1. Those are the two sections that remain before the course is over. Because we are somehow miraculously on schedule, which is rare, that might leave us a little bit of time to have a review day for the final if you want. Let me pull up your syllabus really quickly. Is a good question. If you want to go, you can go. But I do think it's a good question. We can take a second to talk about it. So, right. Actually, we're not quite on schedule, but we're very, very close. So we still need to talk about 5.5, and I'm planning to do that next week, and 6.1. 6.1 is a pretty quick section. That's not going to be hard. And then your final exam is on the 26th. So your final is going to be here. Really? Tuesday? That blows. All right. So your final exam is on Tuesday, the 26th. And we have quite a bit of time between now and then. We're going to finish 5.4 this week. I'd like to spend at least 2 classes on 5.5. That is a challenging section. We can finish 6.1 by next Friday. And then if we follow our normal trend of giving you a full week to prepare between the last bit of new material on a midterm and the midterm itself, that would mean exam 3 is on the 22nd, which would be our last day of class. If you wanted, we could do the last midterm exam 3 on the 20th and leave the 22nd open as a review day for the final. So we'd finish 5.5 on the 15th, review for exam 3 on the 18th, do exam 3 on the 20th, review for the final on the 22nd, and then have the final on the 26th. The 26th must be the final. That cannot be moved. But between doing exam 3 on the 20th or the 22nd, I would be happy to leave that up to you guys. So if you want, let's not make the decision right now, but let's take a poll. All right, let's take a poll in our next class meeting. Mateo, since you're asking, I'll ask you to be responsible for that. If you could just remind me at the start of our next class that we want to poll the class to choose between the 20th and the 22nd for exam 3. And I'll talk back through the two kind of schemes. That would give us the opportunity to leave the 22nd open as a review for the final if you want. Releasing the study guide. Yeah, I can pop the study guide a little bit early. You do have a homework set this week. I opened it up earlier, so you want to work on that. But Friday, I don't mind releasing the study guide like this Friday or maybe next Monday, one of those two. That way you have a little bit of extra time to prep for the test.
What if my I have a final for chemistry on the same day and time as this class?
Yes, Ethan and Isabella. And is there anybody else taking Chem 1 right now with, what was the professor's name? I forget his name.
Baylor.
Baylor. So yeah, there is one chemistry class that has a conflict on the final exam day. I've already talked to that professor and the department chair over there. They are going to offer you guys an alternate time for the final.
So yours is at the same time and theirs will be at a different time?
That's correct. Yep, we're going to stay at this time and Nat Sai is going to move the final. So if you haven't talked with your professor about that, please do talk to him. Yeah, Evan's already spoken with his professor. He's in the same situation. Isabella is also in that situation. I think the professor I talked to mentioned a few other people. Make sure you take the time to talk to your chem professor and get that straightened out. If there's any issues, just have them contact me. But the policy here at Santa Fe is that Nat Sai kind of bends around math for finals. Okay, it might be all Chem 1 finals that do that. So if you're in Chem 1, talk to your chemistry professor. If they give you shit, have them message me. We'll get it sorted out. But the chemistry final should be offered at an alternate time for you guys. All right, that's my wife calling. I got to get going. I hope you guys have a lovely rest of your day, and I'll see you on Friday.